The quiz easier this time. I won't always do that, but this time I did. So let me just, and I almost never do what I'm about to do, but here we go. Did dance? Oh. All right. All right. So I'll go through it quickly. Separate, integrate, but integration requires partial fractions. So that gives me 1/2 3 over x plus 3 plus 1 over x minus 1, which we can integrate. And that gives us 1/2 y squared equals to 3/2 log of x plus 3 plus 1/2 log of x minus 1 plus c. But then I divided c by 2 because, well, you know. And then, so I'm just, my c might be your c over 2, whatever. Or 2c perhaps. But we should all agree on the answers. Anyway, so if I take the square root of both sides, I have to put a plus or minus to be fair. And to be more fair, since y of 0 is -2, I am choosing the minus solution here, right? And as such, I square both sides. That gives me 4 is equal to 3 log 3 plus a constant. This might be your twice a constant there, right? But you should get twice a constant is equal to 4 minus 3 log 3 if you did that. Or you'd say 4 minus, you know, the natural log of 27. And then probably a lot of you are missing this minus. That's kind of the point of this problem, is to make you aware of this issue, right? When we have y squared equals to something, if your initial condition is negative, that means you have to pick the minus radical. Otherwise, you're not going to reproduce the initial condition which is given. So a lot of you probably have the right answer up to that sign, which means, what was this? I feel like it's probably 20 decipoints. Probably, yeah.
Plus or minus, would that count?
What's that?
If we put plus or minus?
No, plus or minus will cost you a decipoint for sure. Probably 20. Yeah, you got to make a choice. This is the I asked for the explicit solution. That means you got to make you got to pick. Yeah.
Okay, so you want. How do you get the 1/2 before you integrate both sides?
How did I get the 1/2?
You have y dy, integral y dy is equal to 1/2 of the long debate right now.
Oh, that's because there's a half and a 3/2 from the partial fractions. I just pulled the half out. Yeah. So there's that one. And of course, you can talk to me in office hours about it if you want to talk more about it. It's all good. But I will take some points off if you don't have the minus, and that's so that you'll remember it next time. Thank you, sir. Let's see here. But you know, everything else being equal, if you only got the sign wrong, you could still have 100% on this quiz, right? Because it's worth 120 decipoints, which is 20 more than you technically need to get the 10 points, which was required here. There's 20% bonus built in. And so this one, you know, I make it look harder than it is in some sense because I'm working with 1 over cosine, well, 1 over absolute value of cosine. And, you know, I think if you look at my solutions in other semesters, sometimes you'll see I don't even put absolute value there. And the reason for that, in part, is what I talk about right here, right? If you're multiplying both sides by the absolute value of a function, if you think through it, it's either all plus, like it's the absolute value of cosine is plus cosine, or absolute value of cosine is minus cosine. So you've got a minus here, here, and here. You just cancel it, right? In other words, we can drop the absolute value without losing any of the calculus here, right? So just, it's really a case, I mean, we're covering both cases at once by multiplying by 1 over cosine. One way to think about it. Anyway, so that gets me to 1 over cosine dy dx plus sine over cosine squared y equal to 1, which is more humanely written as secant x dy dx plus secant tangent y equals to 1, which some of you already would have had because you'd written the integral of tangent as log of the absolute value of secant because you have it memorized, which is fine. Is that the question?
Yeah.
That was actually your question?
No,
Dang it.
Sorry.
Okay.
That was my question. What
All
if,
right.
when you're doing the derivative tangent, you get to the negative ln. What if you just like didn't didn't use a log law and then didn't move the negative in and gave 1 over cosine?
Oh, then I would wonder how exactly you integrated cosine of the exponential of the natural log of, you know, I would wonder how you integrated after that step, because like recognizing that this is 1 over cosine is part and parcel of this being 1 and that being a successful integration. Did you do that integral?
I think so. I think I did it correctly.
Without making the cancellation?
I didn't move the negative inside. And
You didn't move the negative inside. I don't know what that
I
means.
kept it e to the negative ln cosine.
E to the negative ln cosine x. So I mean, see, because at the end of the day, there you're up against multiply the integrating factor, right? Then you'd have, if I'm hearing you right, you'd have cosine of x times e to the minus log of absolute value of cosine x. So you just integrated this.
I attempted this.
What?
Yes.
You attempted it.
Yeah.
I bet it didn't work out though. I mean, I'm just saying, like this, unhappy. This, wait, see, what did that work out to? Oh yeah, 1. This, given a choice, we
first one looks so easy.
we picked that one, yeah. So this is, you guys asked me like, is it always this simple? And no, it's not this simple if you don't do the pre-calculus simplification stuff in the exponential, yeah. No, there's not. You could do that. And so there, you're doing the integrating factor method without deriving it, and that's fine also, yeah? Yeah, so your solution would be totally correct if you didn't go through if you had the insight to see, oh, I should just divide by cosine and that makes this problem work, that's fine, yeah. In fact, that's a more mature solution than mine, yeah.
So on the board, the e to the natural logs, do those operations not cancel out?
No. You have e to the natural log of stuff equals to stuff. E to the natural log of minus natural log of stuff is equal to e to the natural log of 1 over stuff, which is equal to 1 over stuff, which is of course not equal to minus stuff. I should pick a variable other than stuff.
Pac-Man.
Pac-Man, yes. Sorry, I probably, for everyone who's not here at the moment, let me pan over at the moment. You guys talking trash to Austin? Is that what's, yeah. Let's see here. There, we should be good. All right, let me put this away then. Let's get on with our calculus 2. So that's the end of the road here. So, I'm almost done. Sorry, my bad. Could you, Austin, thank you. We missed you the other day. But anyway, so then the reverse product rule, integrate both sides, and then solve for y. Now, if you got to here and put a box around that, that's fine, right? But then integrate both sides. That's, I mean, divide by secant, the same as multiplying by cosine, right? So there's your explicit general answer right there. Anyway, I hope that makes sense. If not, well, study. Let's see here. So at this point, we have reached the edge of the notes I wrote before this semester, right? And we have entered the well, okay, so what I'm trying to get to say here is the material we're about to go into is like really, really different. So there's no like reasonable segue from what we were doing to what we're about to do. It's just radically different mathematics. And well, at the end of it all, we do get back to where we started, and we will find new methods for doing integration and even solving differential equations that we don't currently have access to, all right? But it takes some time. Like, So the pastor at my church was saying that the attention span of a typical child is 65 seconds. The attention span of a typical office worker is 3 minutes. I said, oh, that's really bad, because I try to teach calculus to people for like 75 minutes sometimes. So that means that they maybe understand 5%, if I'm lucky.
We're not typical.
You're not typical. Ah, very good. Very good. But it is true. What we're trying to do in upper level mathematics is countercultural, right? It goes against the grain of our modern society, filled with its sound bites. I mean, good grief, even LUO won't stomach us. Like, oh, you have to have all your videos less than 20 minutes. Like, there's thoughts in here that take 20 minutes, you know? Much less of. So. Oh, I messed it up. Thank you. Anyway, what I'm trying to tell you is you need to be patient in terms of the payoff of the material we're about to get. It's not, I think it's okay. Okay. It's cool. No problem. It's going to take some time for us to get back to the point of applying this to the problems we are already working on. That will happen, but it's going to be a while, all right? So we have to build things up carefully, and the first thing we have to do is to understand what is a sequence. All right, so let me just give you a big sort of bird's eye view of what we're going to do. We're going to talk about what a sequence is today and tomorrow. So a sequence is essentially a list of numbers. We're going to talk about how to take the limit of a sequence. All right, that is a relatively simple project. We'll do that. Then we'll start talking about series. Series are when you take a sequence and you add up the terms. Then the main question is, when you add up all this infinite, if you add up infinitely many terms, does that actually converge to something, or does it blow up? This is a much harder question. And only a handful of problems can we answer that question directly. Most problems we have to take an indirect approach and use what are called convergence or divergence theorems. There's about a dozen of them that we have to learn. That's probably too many. Probably like 6 of them. I don't know. I don't remember. Between a half dozen and dozen theorems we have to learn and be able to apply just to answer whether or not the series converge or diverge. And that's, I think, pretty much where test 2 gets to. All right, test 2 is on differential equations and numerical sequences in series. The interesting part for series happens, in my view, interesting part. Mathematicians would disagree with me about this. But after test 2, we'll start talking about what are called power series. Power series are, well, a professor who was from Texas here used to call power series. He said they're Texas-sized polynomials. These are polynomials without end. So you just keep adding terms. It turns out that that is an incredibly useful object, the idea of a power series. And that will allow us to essentially replace problems that we've currently dealt with corresponding problems for polynomials without end. But polynomials are really easy to calculate with, right? So that's where we're going. Our goal is power series and understanding them and using them and applying them to model functions. But we have to go through sequences and series in order to really lay the groundwork to do those properly. So that's where we're going. That's where we are. So in terms of my notes, I'm working on them. I should have the first batch published pretty soon. I'm about 10 pages into it. I can probably post the part I have on sequences today, and you can use that if you want. But I'm just at the start of the series at the moment, and so just I wanted to warn you about the status of my notes. Now, in the meantime, of course, you're welcome to read Stewart or my old handwritten notes. There's many things you could look at. So, all right, that's just a kind of a view ahead. All right, guys. Here is the attendance sheet. I printed out a fresh one. So, if you could, Jaron, if you could, I'll let you start it. You can add the date up there. All right, so what is a sequence? Let's get started on that. If memory serves me correctly, I think we're in chapter 11 of Stewart. I should probably double check on that. Anyway, so of course, if you have your mission 2, oh man, Well, you guys need to look at page 1 of this again, right? Because page 1 has your recommended homework problems on it, right? But you still have the PDF, so you can look at it. But if you look at there, I've recommended problems from sections 11.1, 11.2, 11.3, 11.4, 11.5, 11.6, and 11.7. Those are the sections in Stewart that we're covering for test 2, all right? Those are the sections which are on sequences and numerical series. The power series comes at the very end of the chapter. So anyway, here it is. Let S equal to n0, n0 plus 1, n0 plus 2, comma, dot, dot, dot. So what we're looking at here is a subset of the integers. Do you guys know what integers are? Z is what? 0, plus or minus 1, plus or minus 2, and so forth, right? So it's all the positive, all the negative numbers, and 0 as well, right? So here I want to say let S be a subset of the integers that has the property that you have basically you have the first point in it, right? And then you have every point after it, plus 1, all right? So it's like that. Then a function A from S to the reals is called a sequence. I mean, more specifically, this is a real sequence, all right? And our notation is this. We typically write A of n equal to A sub n. So like our typical function notation is A of n, right? Like f of x. But for our purposes here, it's more convenient to use a subscript for the argument. So we write A sub n instead, right? And we refer to A sub n as the nth term in the sequence. This is the nth term. Nth term in the sequence. And what else can I tell you? We also sometimes write we write this, right? A sub n equals n naught to infinity. All right, so this is another way of expressing the sequence. You can basically express the sequence as a list of its values, right? Like this. We could say it's what is it? The sequence is a list, right? It's A sub n naught plus 1, A sub n naught plus 2, dot, 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 dot. Right. So I guess I should, comment. A lot of mathematicians, right? Well, let me just say this. Usually, we have n naught equals to 1 or n naught equals to 0. Like a lot of times, the first number, the first thing that appears is just either 1 or 0. Now, if we have n naught equal to 1, that makes this set S just the natural numbers. The natural numbers are 1, 2, 3, 4, like that in here, right? If we have n equals to 0, we have, that would make my S, quote unquote, like the natural number 0 unioned with the natural numbers, all right? Anyway, so the larger point here is that the domain of a sequence is a subset of the integers, and it's a rather special kind of subset. It's a subset that has a start but doesn't have an end, right? And it also has this so-called successor property. If you have, a number in it, the number plus 1 is also in it, right? But only whole numbers. So far, so good? All right. By the way, I should also mention n is the index. That's the name of n. It's the index here of the sequence. And the index, it's not written in stone either, right? Like, let me give you an example. If a sub n equals n squared, all right, for n in the natural numbers, then you can write the sequence as a sub n equal to 1. What comes next? 1 squared is 1, right? 2 squared is 4, 9, 16, 25, 36. Well, you get the idea. And so, so sometimes if I'm being lazy and it doesn't matter too much, it's clear from the context where the sequence starts, I write it like that. But it's better, it leads to less trouble if I instead write this as this. A sub n, n equals 1 to infinity, write that, like that. So here I'm announcing the, the starting point and the fact that it's a sequence. Now, it's not, to be a little bit more precise about the data type we're working with, it's not just a set of values, right? It's not a set of values in the sense that, if I take these two and switch them, that's not the same sequence, right? It's an ordered list. The order matters, all right? So not just a set, it's an ordered list. But I would say this, if I wanted to, I could let like bk equal to k squared. Then if I look at, bk, k equals 1 to infinity, well, that's the same, it's b1, b2, which works out to, again, 1, 4, 9. So in this sense, the n is just a placeholder, right? Like it doesn't have an independent meaning in some sense, right? It's all wrapped together with the formula. You could use a different letter to describe the same sequence, right? This is analogous to the thing we have about functions, right? Like you could write, I could tell you f of x equals x squared, right? Or I could tell you that f of theta equals to theta squared. If these two expressions have the same domain, they are the same function, even though I used a different letter to express them. Right? That is still true for sequences, but now we can use a different index if you want. All right, so that's one thing. Let me make less silly comments. Here's one. So let's actually put that into practice. This freedom to change the index. If we have a sub n equals 1 to infinity equal to 3, 4, 5, 6, and so forth, right? On the other hand, I've got b sub k for k equals to 3 to infinity equal to the same thing. So I would say in some sense those are the same. Well, this is where the language gets a little dicey. They are the same ordered list, but technically speaking, they're not the same sequence because this one starts at 3, whereas this one starts at 1. And a sequence is a function, and a function is tied to its domain, right? I can't just willy-nilly change the domain of a function and say it's the same function, right? But they are the same ordered list. What's the formula for the first one? an equals to what? What'd you guys tell me? 2 plus n? I heard n plus 2. Which is it? Either way is fine. I mean, 2 plus n is n plus 2, right? Agreed. The formula for bk, what's that? Have it your way, right? Let's see here, bk. My way is for my burger not to be cooked with fake meat. So that's why I don't eat there anymore. Anyway, what's that? Equals n. No, we can't use n. Okay, right, yeah. But, I mean, saying it equals n is the right spirit of things, but I'm stuck with k as my index here, right? So, if that's okay with you guys. All right, so, oh, I'm sorry. That was horrible. Anyway, so example 3, we can talk about recursively defined sequences. What's that about? So here's what we'll do. We'll say a sub 0 is equal to 1, all right? And then we'll say a sub n is equal to, well, a sub n plus 1, I'll do it this way. A sub n plus 1 is equal to n plus 1 times a sub n for n equals 1 to dot, 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 right? Let me just tell you a little bit of language here before I go on, because I know some of you are still learning like mathematical language. I mean, that is a lot of what you're going to have to learn here, right? So you're like, I understand the math, I just don't understand the jargon. You need to understand the jargon. You need to learn the jargon. That's like part of the course, all right? So you should be comfortable with the distinction between, say, writing this and writing n is an element of the natural numbers. Those are the same sentence. So to say n is an element of the natural numbers is to say that n is equal to like 1 or 2 or 3 or something in there, yeah? Those are equivalent statements. Okay, anyway, this is a recursively defined sequence. So let's work it out. What is well, a0 I gave you, right? What's a1? 0 plus 1 times a0, right? Put n equals to 0 there. Aw, man. Man. Curses. All right, there's two ways to fix this. I'll have to see. This is what I get for saying like what I just said. Anyway, so if I could understand my own, right? So union with 0 and start with 0. My bad. See, the other option, I could have changed the formula, but I left the formula alone. Okay, so anyway, there's different ways you could set up the recursion, right? Okay, so that set. Put in n equals to 0, we get this, which is what? 1 times 1, which is 1, right? How about a2? We get 2, yeah, sorry. It's the same number here and here, right? So 2 times a1, which is 2. a3, 3 times a2, which is 3 times 2, which is 6, right? a4, 4 times a3, which is 4 times 3 times 2, which is 24. a5, which is 5a4, which is 5 times 4 times 3 times 2, which is 120. a6 is 6 times a5, which is 720. a7 is 7 times a6, which is 5040. a8 is 8 times a7, which is 40,320. Okay, that's all I know. But anyway, yeah. This sequence is, if I'm recursively defining a sequence, all right? So if you were to calculate it here, a sub 100 would be 3, 0, 4, 1, 4, 4, 1, 4, 0, 9, 3. Me reading numbers for about a half a minute, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 trailing zeros. Anyway, like when you have the notes, it pretty much takes the full. This is the biggest one I could do. And hey, wait a minute. That's not 100 factorial. That's 50 factorial. Sorry. Oh, wait a minute. I just spilled the beans. What is this thing called? Factorial, right. In fact, definition, a sub n from the last thing is what we call n factorial. In other words, you can define the factorial as this. 0 factorial is 1, and n factorial is equal to n times n minus 1 factorial. That's for n in the natural numbers. So if I define the recursion like that, then I could have started with 1 rather than 0. But anyway, this is the factorial function. It's a sequence. Now this sequence is, you know, this is maybe, I don't know if you guys have seen this. Show of hands, who's seen factorial before? Okay, good, good. So is that, where did you see it? I'm curious. YouTube? What's that?
BC calculus and stats.
BC calculus and stats. Okay. Yeah, it might, if you cover like probability and statistics, it should have come up, right? All right, so there's that one. Example. Let's see here, where am I? Wait a minute, you guys got to stop me if I'm out of time.
Oh, you're out of time.
Am I out of time?
Yeah, always.
It's 9:20, right? 10:10 class ends, right?
Yeah.
Yeah, you guys should stop me. Let me just go on like that. You owe me money. I only work till 10:10. You guys took 3 extra minutes of my life. How dare you?